Okay, so this week it's all about statistics. We're starting chapter 6. Again, if you are just watching this video, this is the textbook that I'm using, and we're starting chapter 6, which is all about statistics. Okay? I know some of you have seen statistics before and things like that, so we're just going to go over a couple things. We essentially assume that we have some random variable, and we call it x, okay? If you're rolling dice, right, then your x is discrete. And the reason why it's discrete is because I can only roll the numbers 1 through 6, okay? I can't roll any other numbers, no zeros, no negatives, no fractions, no irrational numbers, no nothing. It has to be 6 specific discrete random variables. Because of that, there are some interesting things that I'll talk about later. If you are, measuring, say, acceleration from accelerometer, then your measurand is continuous, okay? And so if you're using like an Arduino or a circuit playground and you're measuring the acceleration, if you just leave it on a desk, you're going to get, like 9.81 plus or minus some random noise. But you can basically get any number from the range of the accelerometer. So if we imagine we have like, this omnipotent accelerometer that can measure minus infinity to positive infinity, we basically say we have, all of the numbers in between there. We can measure any acceleration between there. Now, typically this is not true, and we can only measure like I think the circuit playground is like 2 G's, so it'll be like minus 2G to 2G, and we can only measure the continuous variables in between that range. But that doesn't matter. The point is that I can have a continuous variable that's in between those. Okay. Now there are some things that are the same between random and continuous. Okay. So the first one, and I'm sure you've seen this before, is the mean mu of the random variable. And this is the sum of all of the different samples divided by n, 1 to n. Okay? So if you have an example and you roll a dice and you get like a 1, a 4, a 3, a 4, a 2, a 1, you just roll the dice. I would imagine that if you rolled a dice an infinite number of times, your mean would be 3 or 3.5. I don't know, maybe you can write a computer program. I feel like you should get something in between. But anyway, if you have discrete numbers like this, the mean would be the sum of all of these. So first of all, so this is x1, x2, x3, x4, x5, x6. So that means I'm doing 6 samples, so n is 6. And so if I wanted the mean, that's 5, 8, 12, 14, 15. So it'd be 15 over 6. That is the mean, and I don't really care. You don't have a calculator on a test, so I don't really care. But anyway, that's the mean, 15 over 6, or whatever that is. That is the mean of the samples. If you have a random variable, if you're just sampling data, and you're getting data like, 9.81, 9.74, 9.78, 9.82, then again, here are your samples. You have a discrete number of samples, so in this case you have 4 samples, n equals 4. And your mean would just be add up all of them and divide by 4. Okay, you've seen this before. It's very, very simple. Okay, so this is the mean. This is one of the things that you probably need to, know if you know statistics. Okay, the median, so this is number 1. Number 2 is the median. And the median, I'm just going to read from the textbook here. It is if you arrange the numbers in ascending to descending order, it is the value at the center of the set. Okay? So in this case, if I arrange these in order, I would get 1, 1, 2, 3, and 4. And so the center is 2, so my median is 2. Over here, if I arrange these in ascending order, I would get 9.74, 9.78, 9.81, and 82. And so here, and here, and here. And so the median for this would be the average of the two, okay? So it is the center of set in order, okay? The second one is the mode, okay? Now, this is where random and continuous change here. So the mode is the value of the variable that corresponds to the peak value of the probability, okay? So I only sampled this 6 times, and so this is pretty poor, but the mode is actually 1 in this case for this discrete set because I sampled that one the most, okay? So it's most / peak samples, okay? Now you have to consider, I got a repeat here because there's only 6 possibilities. I mean, if you have a 1 in 6 chance of rolling a 1, then it's going to be pretty likely that you're going to roll another 1, right? If you have a continuous variable from -infinity to infinity, it's going to be, because you're sampling something on a real machine, it's possible that you'll get the exact same number, but statistically, you have a 0 probability of getting the exact same number again, because continuous variables are continuous. Like, yes, this is 9.81, this is 9.82, and you're like, oh, those are almost the same, but really this is like 9.82000015, whatever. There's a bunch of trailing digits. We're only looking at the first 2 significant figures, but if you have a truly continuous random variable, you have a 0 probability of sampling the same one. Or at least that's sort of the idea. Or the correlation between numbers drops to 0. And so you don't really have a mode, but if you make a histogram, and it looks like there's some plots over here, if you make a histogram of this data, so say you say the numbers between, let's just say I have buckets like this, 5 and 6. How many times did I sample 1? Twice. How many samples did I sample? 2, once, 3, once, 4, twice. And actually, I didn't even realize that. It looks like we have a competing mode here. And I'm not entirely sure what to do about that. But in my opinion, I think this means you need more samples because at some point you would get something. Actually, I think rolling a dice is uniform, right? So I think this would happen anyway. Yeah, I think rolling a dice is a uniform distribution. Sampling the accelerometer is probably Gaussian, so you'd probably get a completely different curve. But that's for another lecture. The point is that if you do the same thing for a continuous variable, you're going to get a histogram, in my opinion, you're going to get something that looks like this. It's not going to be perfect, it's going to be noisy, but you're going to get, I would hope, the peak value of 9.81 if you just have the accelerometer sitting on the desk. And so the median is the center of the set, the mode is the largest peak. This is a uniform that's perfectly symmetric on either side, which means it's not skewed. It's possible to have a distribution that looks like this, right? So that's skewed. So the mean is going to be here. The median is going to be halfway in between, right? The median is going to be here, but the mode is going to be over here, right? That's the most sample. So you can see how things kind of change depending on which one you grab. Okay? So mean, median, mode, and then the last thing I want to do in this video, so here's mean, right? There's a formula for mean. Median is here, mode is here. The last thing I want to do is the standard deviation, sigma, and that is I'm going to do sigma squared because I hate the square root. It is the sum of I equals 1 to n of the samples minus the mean squared over n. And again, here, because it's xi minus mu, you actually have to compute the mean first before you can compute standard deviation. Okay, so this is number 4. Okay, so typically when you're sampling data, if you're measuring analog signal from a pitot probe, or if you are measuring an accelerometer, or if you're measuring speed, typically the variable is going to be rather noisy. You want to sample the data for, say 100 samples, however fast your thing is going. If you have like a 2,000 hertz sensor, why not just sample 2,000 data points and then average them all together and make that your value. If you can handle 1 second of delay, just take as many data points as you can, right? Because the larger your sampling distribution, the more accurate you are. Okay, and so your mean will tell you the center of your distribution, and the standard deviation will tell you, how wide and how distributed your system is. Okay, I think that's all I want to do for this lecture for statistics, and then we'll talk about probability mass distribution functions on Wednesday. Okay, I hope you enjoyed this lecture. Post in the comments if you have any questions.